effect. Okay. And what I had told you, that when an atom is placed in an external magnetic field, the energy levels get shifted, and that this phenomena is known as Zeeman effect. And for a single electron that we are talking about, the interaction Hamiltonian, or the perturbation which we are calling, okay, this is equal to minus mu L dot B external minus mu S dot B external, where we are getting contribution from magnetic dipole moment associated with orbital motion and the magnetic dipole moment associated with electron spin. Therefore, this is the magnetic dipole moment associated with electron spin, and this is the dipole moment associated with the orbital motion, where mu L is minus E by twice m L and mu S is minus E by m S, such that this Hij, this is equal to E by twice m L plus twice S dot B external. This was the expression which I wrote yesterday, and then I told you that we have already an internal magnetic field because of the motion of the proton around the electron, and then we have this external magnetic field. Now it depends whether external magnetic field dominates over the internal magnetic field, or internal magnetic field dominates over the external magnetic field, or they are all of equal magnitude or comparable, such that you cannot ignore one in comparison to the other. But what we are interested today is to discuss weak field Zeeman effect. Okay, what we are interested today is to discuss weak field Zeeman effect. Weak field Zeeman effect means that the internal magnetic field, because of the motion of the proton, is greater than the external magnetic field that we are applying. Okay, and that means the fine structure dominates. Fine structure dominates, and this interaction Hamiltonian that we are considering, that is arising because of the external magnetic field, this may be treated as a small perturbation. That means L dot S part is being dominated, okay, and since that part is being dominated, this means that in the presence of a spin orbit coupling L dot S, L and S are not separately conserved. This we have seen yesterday. And if this is so, then the good quantum number that we talked about, where NL, J and NMJ were the good quantum numbers. since L and S, they don't commute with L dot S, therefore the quantum number associated with L, that is ML, and the quantum number associated with S, that is MS, they are not good quantum number. The system would be described by N, L, J, Mj. Therefore, the interaction energy that we obtained is the expectation value of the wave function described by N, L, J, Mj, H, I, Z, N, L, J, Mj. And that means if you look at this, if I put instead of Hij, this expression, that means we are supposed to get the expectation value of L plus twice S. Okay, therefore this is equivalent to getting an expectation value of L plus twice S. Now our task is to obtain the expectation value for L plus twice S. Okay. Now L plus twice S, we can write it as L plus S, and that is equal to L plus S is total angular momentum J plus S, and we know that for J, the quantum number associated with this Mj is a good quantum number, and we don't have the expectation value of S. But what we do, instead of obtaining the expectation value of S directly, we obtain the average value of S. Okay, instead of obtaining the expectation value of S, we obtain the average value of S. And average value of X is defined as the projection of S along the direction of J. Okay, therefore instead of S, we try to obtain average value of S, which we represent by S average, and this is defined as the projection of S along the total angular momentum J. Okay, and in vectors we know that how a projection is defined. Projection of A along the direction of B. Okay, and since this quantities are, and this we write it as A dot B upon mod of B, and that is A dot B upon simply B. This is how we say that this is the projection of A along the direction of B, and if this is a vector quantity, then this average we define it as S dot J upon capital J in the direction of J. Okay, and that means since this should be a vector, S dot J, unit vector J, we can write it as J upon, same like this we have written here, J upon mod of J, and 2 mod of J will make it J square. Therefore, what we are supposed to evaluate is S dot J upon J square times the total angular momentum J. Okay, and expectation value of this would be obtained by getting the expectation value of this quantity. Okay, expectation of value of J is well known, that is Mj in units of H cross. Okay, that means now we are supposed to obtain the expectation value of S dot J. if you can recall, we have already obtained in one of the class the expectation value of L dot S. Similarly here, when we try to obtain the expectation value of S dot J, we start with the total angular momentum. J is equal to L plus S, and then we write L is equal to J minus S, such that if I square both the sides, L square will be equal to J square plus S square minus twice L dot S, minus twice, sorry, J dot S. L is J square plus S square minus twice J dot S, such that J dot S is equal to J square plus S square minus L square. And that means J dot S is nothing but J square plus S square minus L square by 2. Okay. Now we know that J square, when operates on psi, the eigenvalues that we get is J plus 1 H cross square psi. Similarly, S square will, when operate on psi, it will give you SS plus 1 H cross square, and this will give you LL plus 1 H cross square. Therefore, this implies that J dot S or S dot J, since this is a scalar product, we can write it as S square by 2. I have taken H square common because for every eigenvalue I will have, they are measured, angular momentum are measured in units of H cross. Therefore, H cross will be throughout our expression, minus SS plus 1 minus LL plus 1. This will be J dot S. This will be the expectation value of J dot S, H square by 2, J plus 1, SS plus 1 minus L plus 1. Since we are talking about a single electron, therefore for that S will be equal to half, such that SS plus 1 will be equal to 3 by 4. And this would lead to J dot S is equal to H square by 2 J plus 1 minus LL plus 1 plus 3 by 4. This will be our J dot S. Okay. We have evaluated this quantity. Okay. And then we were supposed to evaluate expectation value of L plus twice S. This we wrote it as J plus S. Okay, this we wrote it as J plus S, and J we have obtained, this S we have obtained in the present case the average value of S dot J. We know what is this J square. This will be J plus 1, again H cross square, and this J, this will give us the eigenvalue MH cross. Okay, therefore we know S dot J, we know J square, we know this J. Therefore we can write this guy as, see here, if you notice, in the average value of S also we have a J around, and then we have S dot J upon J square. Therefore I can write this as J I will take outside, because one J is here and another J I will get from this place, 1 plus S dot J by J square, and then the average value of J. Okay, and this will be 1 plus S dot J we have evaluated. This is everywhere I should put like this. 1 plus S dot J, this is H square by 2 JJ plus 1 minus LL plus 1 plus 3 by 4 upon JJ plus 1 H cross square. And what is this J? J is nothing but MH cross. J is nothing but MH cross. Okay, this J, I am still continuing with it, but later I will put it J, this J as MH cross. Now this quantity in this square bracket is known as Landau G factor, and it is represented by G factor, and it is represented by Gj. Okay, so therefore this quantity which is in the square bracket is known as the Landau's G factor. Okay, this is represented by Gj. Now we go back, and what is this J? This is, remember, this is MH cross. This is nothing but this is MJ. Well, if we want to directly associate M with this total J quantum number, there we will put a suffix J with M. Therefore, I am changing the slide, and or let me just write it on this side. Now we have the expectation value of L plus twice S. Now we go back to the expression for the interaction energy. This was E by twice M B external dot expectation value of L plus twice S. Okay, we have evaluated this quantity. We know each one of them. Okay, therefore this will be equal to E by twice M B external. Then what I am telling you, that you can call this as Gj, and then J is being measured in units of MJH cross. Okay, this MJH cross is associated with the expectation value of this capital J. Now this H cross I will bring to this side. This will become EH cross upon twice M B external Gj Mj, and this EH cross upon twice M we call by the name Bohr magneton. This is nothing but Bohr magneton. This is represented by mu B. Okay, therefore the interaction energy is how much? Mu B Gj B external Mj. This will be the interaction energy when you place an atom in a weak external magnetic field. Weak because weak in comparison to the internal magnetic. Weak in comparison to the internal magnetic field. Now the important point is, if for example, if I am talking about the ground state, then the ground state corresponds to n equal to 1, principal quantum number n equal to 1. For n equal to 1, what is the value of L? The value of L is, for n equal to ground state, how much will be the shift? This n is 1, then L is 0, and L is 0, but the spin of the electron is half. Therefore, my J will be how much? J will be half, and if J is half, your Mj will be, it will go from minus half to plus half. This Mj will go from minus half to plus half. Okay. Now for this value of n equal to 1 ground state, L equal to 0, S equal to half, how much is the Landis G factor? If you notice, the Landis G factor, H square, you can directly cancel with here, with this H square in the denominator. J plus 1. J plus 1 is half plus 1 minus 0 plus 3 by 4 1 plus upon half plus. Okay, this is Gj, the square bracket. And how much is this much? This would be, this will also turn out to be 2 plus 1, 3 by 4 plus 3 by 4 upon 3 by 4. Therefore, here you have 3 by 4 upon 3 by 4. And then we have a factor of 2 hanging around here to this place. Therefore, overall, this would be how much? One plus 6 by 4 upon 6 by 4 upon 3 by 2. Is it not? 6 by 4 upon 3 by 2, and this will be how much? 1 second. J plus 1 minus LL plus 1 plus 3 by 4 upon J. Gj will turn out to be equal to 2. Okay, Gj will turn out to be 2. Okay, if Gj is 2 and Mj is plus half or minus half, Mj is plus half or minus half, Gj is 2, then that means this is how much? Plus minus 1. With Gj, which Mj, if you take these two together, this will be how much? Plus minus 1. And that means this quantity will be plus minus mu b, B external. Mu b is the Bohr magneton. This value is constant. Okay. B external, the external magnetic field that you apply. Therefore, you know that how much will be the energy shift when you apply an external magnetic field. And since this is a perturbation, okay, therefore if somebody asks you that how much will be the total energy when you have of the hydrogen atom placed in an external magnetic field, the total energy of the hydrogen atom placed in the external magnetic field, the contribution will come from H naught, the pure Hamiltonian, plus the hyperfine splitting part, which has contribution from relativistic corrections as well as from a spin orbit correction, and then this external magnetic field. Now, if you put all them together, from the pure Hamiltonian part, we have minus 13.6 electron volts. This is for the ground state. That is why in the denominator I am not writing N square. Plus, we have seen yesterday, this will be 1 plus alpha square by 4, and then plus minus this mu b bx. This will be the total energy that would be possessed by the hydrogen atom when the hydrogen atom will be placed in an external, the hydrogen atom will be placed in an external magnetic field. Okay. Similarly, you can do the calculation which has been done in the Griffiths book. What will happen when you place the hydrogen atom in the external magnetic field, but the magnetic field is, external magnetic field is very strong in comparison to the internal magnetic field, and that means now the small perturbation would be the spin orbit correction, L dot S. Okay, therefore the quantity that will be important for you will be the expectation value of J plus S that would dominate. Okay, but I don't think that is required to be done. Once you understand that how we perform calculations when you switch on the external magnetic field. Okay. Now let us come to the another topic of today's lecture, and that is the variational principle. Now, what I have told you while introducing perturbation theory, that most of the problems in quantum mechanics or in real life, they cannot be solved exactly. A few of them we are able to solve, but most of them we are unable to. Then some of the problems we solve using approximation methods, and there are few approximation methods like perturbation theory, like variational principle, like WKB approximation. Now, for perturbation theory, we saw that actually it is the H naught part which should dominate, and the perturbed part should contribute a little. That would be only correction. But there are systems where you cannot separate it into two categories, the pure Hamiltonian part and the perturbed Hamiltonian part, and you say that perturbed Hamiltonian part is the small correction. Therefore, there are limitations to perturbation theory. Then we have the variational principle, which is there in your course. Then we have WKB approximation, Wenzel, Kramer's, Berlioz approximation method, which is not there in your course. But still, with these approximation methods, we are only able to solve a limited number of problems. Due to the scarcity of solving real life problems using these methods, then we switch over to the models or further approximations. Okay, but today what we are going to discuss is an approximation method which is known by the name the variational principle. And this variational principle, in very short, it is a trial method. Okay, it is a trial method. What is it? What we mean by trial method? That we start by making guess regarding the wave function. Now, the most important part of quantum mechanics is to get the wave function. And from B.Sc final to M.Sc till now, you have seen that it is really very difficult to get the wave function. In the case of harmonic oscillator, we have seen, or in the hydrogen atom or other places, it is very difficult to solve the short time independent Schrodinger equation to finally, because that is a differential equation. You use Legendre, Lagrange, associated Legendre, Bessel's, etc., etc., methods to obtain the solution which finally gives you an expression for the wave function. But here what it says that you start with the wave function. You start with the wave function. That means you know the solution. And that is, in principle, if it had been so easy to write the wave function, then there was no need of solving all those differential equations. Okay? Therefore, this is an approximation method where you want to obtain the ground state energy for a system described by a Hamiltonian H, and we are unable to solve time independent Schrodinger equation. Then this method tells you to guess the wave function and obtain the upper bound for the ground state energy. Okay, what it tells you, suppose you want to obtain the ground state energy for a system described by Hamiltonian H, for which you cannot solve time independent Schrodinger equation, then it tells you to guess the wave function. Then it tells you to guess the wave function and obtain an upper bound for the ground state energy. For the ground state energy. Upper bound. That is important. That means for a wave function psi, what it tells you that E ground state is less than or equal to the expectation value of H. For a wave function, psi E ground state is less than A. That is why it tells you that it gives you an upper bound for the ground state energy. Now what I am telling you, that really it is very difficult to make a guess for the wave function, and therefore what one does, one tries with several wave function. For example, if I have been asked, can I change the slide?
Yes, sir.
Okay, suppose I have been asked to give the solution for the ground state. ये हम लोग को कब रिकनेक्ट करना पड़ेगा अभी. For the ground state energy, for a system using variational principle, using variational principle. Okay, it is better that we reconnect